Welcome back. Today our topic of discussion is going to be the unit circle, which is quite literally a circle of radius 1, hence the word unit. So if I have a circle, put it in the xy coordinate system, and I say that the radius is equal to 1, then that means the equation is going to be x squared plus y squared equals 1 squared, which is simply 1. And you can see here in my calculator that I have an x squared plus y squared equals 1 graph with a point here and a point here on the circle labeled. So it turns out there is an immediate advantage to having a unit circle, and that is that if I take the arc length, which hopefully remember from last time is s equals r times theta in radians. Well, if r is 1, then s just becomes equal to theta in radians. So that means the arc length is the same thing as the angle measured in radians. So let's see what that means on this graph. So what I can do is I can add a segment right here to there, lock on, and then I will add a circular arc. There we go. From here to here to there. Okay, cool. We have the circular arc. Now what we're going to do is add some measurements. So if I put a measurement for the directed angle from here to there, you see that this 1.2559 radians is the angle measure in radians. And then let's add a length for the arc. So if I hover over here and hit tab, then it allows me to highlight the circular arc. And you notice immediately that the arc length measure 1.2559 is the same as the radian measure of the angle, like I asserted here. Now, in fact, we can even take this and grab this point and move it, and notice that always the arc length and the angle are the same value. And I can keep going all the way around the circle, and you see this is how it works. Cool. Okay, so I'm going to put it back here. That's the deal. So what we want to do is we want to represent both of these simultaneously with a single variable just to make life easier. So we say we will call this the variable t, and t will be a real number. And this is going to be the one variable that keeps track of simultaneously our arc length and our angle. It can refer to either one. And since we have a circle with this very specific equation, we have a set of combinations of x and y that are going to satisfy this equation, namely those are the points on the circle. And so if I engage the idea of an angle and say in standard position, so I'll start from the positive x-axis, let's put the terminal side of this angle right there. And remember, t can represent either the arc length or the angle measure in radians. And let's say that the terminal side of this angle intersects the circle at a point P with coordinates x and y. So in this calculator screen, what I'm going to do is I'm going to hit menu and then geometry, points and lines, and I'm going to hit point on. And then I'm going to hover over this point. It'll lock and select this, and it'll pull up the coordinates of that point. So I can see this. Now, so we can tell that for this point, if the angle measure is given by t equals 1.2636, and I'm not going to bother writing radians. We understand that this is either radians for the angle or it's just length units for the arc length. The x coordinate and the y coordinate are given 0.30237 and 0.95319. Okay, and of course I can grab this point and I can move it around, and you can see that the x and y coordinates change. The x turns negative when you go into the second quadrant. When you go into the third quadrant, now the y coordinate turns negative. And then when you go down here into the fourth quadrant, the x coordinate becomes positive again. Okay. So overall, we have this concept of the x coordinate, the y coordinate, and the angle measure, which is represented by the variable t. So now it's time to define some functions. So we give a function the name sine, and we write it as sin. And the input variable, the argument, is going to be this t, which represents the angle measure or the arc length measure. We're going to define this as the y coordinate on the unit circle, which perhaps in this context we can simply say sine of t equals y to understand that relationship. So what that actually means here is if I wanted to write sine of 1.2636, then this should get me, according to the definition, the number 0.95319. Or alternatively, you see on the screen now, I have a different point, right? If I were to take sine of, the angle is 4.9973 radians. So if I type 4.9973, then this should give me a y-coordinate of negative 0.95968. And in fact, separate from the graph, if I make a new calculator page and verifying that my mode is in radians, I can actually type in sine of 1.2636 and verify that that is indeed the number I get. I can also verify sine of 4.9973, and that is indeed this number. So somehow the calculator is understanding how to generate the y-coordinate on the unit circle by using an angle. Okay, so we have the y-coordinate. Now let's go to the x-coordinate. We're going to call a function cosine, and we're going to write it as cos. Cosine, the input variable, the argument, is t, and this is going to be the x-coordinate on the unit circle. So we could write this as cosine of t equals the x-coordinate, and if we go back to our picture, then we know from what we did earlier that when the angle variable is 1.2636, I could write cosine of 1.2636. This will equal the x-coordinate for that point, which was 0.30237. And then if we were to take cosine of the angle that's now displayed on the screen, that 4.9973, we should get the x-coordinate of the point right here, which, looking in the upper left-hand corner, is 0.2811. Now, we can go back to the calculator page and actually verify that this is a thing. We can type in cosine of 1.2636, and it should come out to be this number. The calculator understands what to do. And we can also verify this value, 4.9973, that right there. So somehow, there's a way that the calculator is looking at certain angles on the unit circle, figuring out what the x and y coordinates are, and presenting them to us in the form of cosine for the x-coordinate and sine for the y-coordinate. So far, for the case where the terminal side of an angle t intersects the unit circle at a point x comma y, we have a function called sine, which is defined as sine of t is equal to the y-coordinate, and we have another function called cosine, where we write cos to say cosine. Cosine of t equals x. Well, it turns out there are a few other trigonometric functions that we define, sort of for completeness, convenience, whatever you want to call it. There is one called tangent, and we write this as tan, tangent of the t variable, and this is going to be the y over the x. This is going to be sine over cosine. And then there's this thing called cosecant, which we write CSC of t, and this is going to be the reciprocal of sine. So this is going to be 1 over y. And then there's the secant, SEC, so secant of t. This is going to be the reciprocal of cosine of t. So this is going to be 1 over x. And then finally, cotangent, which we write COT, cotangent of t, is going to equal the reciprocal of tangent of t. So we're going to have x over y. And these have geometric significance as well, but that will be a topic for some other time, not today. What you really, really need to know at this stage, these two. And remember that everything is related to the y-coordinate and the x-coordinate by these definitions. But most importantly, you should be familiar that sine of t is the y-coordinate and cosine of t is the x-coordinate. So as an example of this, let's imagine we have a circle. It's a unit circle. We've got x and y, and we want a very specific angle. And I'm not so interested in exactly what that angle is right now, but I'm interested in the place where it intersects the unit circle. So let's just say this angle is t. And this point right here, P, has coordinates negative root 3 over 2, comma, positive 1/2. Now, if I wanted to know sine of t, we understand that that's going to be the y-coordinate of this point. I don't know the angle t yet, but I can still say that sine of whatever that angle happens to be is 1/2 for the y-coordinate, just because I know where it intersects the unit circle. Okay. If I want cosine of t, I would say that must be the x-coordinate of that point, so this would be negative root 3 over 2. And I could say tangent of t would be the y-coordinate over the x-coordinate, so that would be 1/2 divided by negative root 3 over 2, which I can write as 1/2 times the reciprocal, negative 2 over root 3. The 2's cancel, and I get, once I rationalize the denominator, negative root 3 over 3. If I want to know cosecant of this angle, then cosecant is 1 over the y-coordinate, so that would be 1 over 1/2, also known as 2. If I want secant of t, then this would be 1 over the x-coordinate, which is 1 over this value. Rationalizing gets me negative 2 root 3 over 3. And then finally, cotangent of t will be x over y, which is the reciprocal of tangent of t, and the reciprocal of this is simply negative root 3. So the way we would perhaps phrase this question is, given this circle, given this angle, given this point where the terminal side of the angle intersects the unit circle, it might be, find the values of the 6 trigonometric functions for the angle shown. So it's a very strange idea because we don't know the value of the angle, but that's not essential to us. All we need is a point on the circle, and then we can figure out the values of sine of that angle, cosine of that angle, tangent of that angle, cosecant of that angle, secant of that angle, and cotangent of that angle simply by using these definitions and the x, y coordinates of the intersection. So now this raises another interesting question. What if we want to know something like sine of pi over 4? There's a very specific number associated with this, and perhaps we can come up with a way to figure out what this is. Well, in order to eventually get there, we're going to start with 2 special triangles. So the first special triangle is the isosceles right triangle. So isosceles means these 2 sides are the same, which forces these angles to both be 45 degrees in order for the angles to add up to 180 degrees. And so what we're going to do is we're going to say, let the hypotenuse equal 1 for reasons. And if we let the hypotenuse equal 1, then we know this side and this side are both the same value. Perhaps I will assign both of them to x. And by the Pythagorean theorem, I can say that x squared plus x squared is equal to 1 squared, which makes this 2x squared equals 1, which means x squared is equal to 1/2, which means that x is equal to the square root of 1/2, which I can rationalize the denominator to make root 2 over 2. So I can erase this and understand that these sides are both root 2 over 2 apiece. Okay? Then I can make another triangle. This is the equilateral triangle, where all the sides are the same as each other, which forces all the angles to be the same as each other. Now what I'm going to do is I'm going to label each of the sides with length 1. And I'm going to take this angle at the top and I'm going to bisect it, which will create 2 congruent triangles, which means this angle and this angle are congruent to each other, and they add up to 180 degrees, so they must each be 90 degrees. Okay? And furthermore, I understand that this side is a half because 2 congruent sides have to add up to 1. This ends up being the midpoint. Okay? Now, I would like to find this height right in here. So I'm going to go ahead and call this x, and we can say 1/2 squared plus x squared equals 1. And then this will be 1/4 plus x squared equals 1. So I subtract 1/4. I get x squared is equal to 3/4. If I square root, I will get x is the root 3 over 2. And perhaps I can then replace this with the square root of 3 over 2. That will be this side right here. Now let's talk about what we can do with these triangles we've created. To summarize our results, if we have a 45, 45, 90 triangle, then if the hypotenuse is 1, each of the legs is root 2 over 2. If we have a 30, 60, 90 triangle, which we got from cutting an equilateral triangle in half, this orientation has 1/2 and root 3 over 2 if the hypotenuse is 1. And this orientation has root 3 over 2 on the height and 1/2 on the base. Okay. So now we would like to take the unit circle, and taking careful note that the radius is 1, I can take this triangle and squeeze it right into here. And this angle right here, 45 degrees, is the same as pi over 4 radians. And since the hypotenuse is 1, I will have this is the square root of 2 over 2, and this is the square root of 2 over 2, which will make this point root 2 over 2, comma, root 2 over 2. Which actually means then, I can say for this angle that sine of pi over 4 is equal to the y-coordinate, which is square root of 2 over 2. I can say cosine of pi over 4 is the x-coordinate, which is square root of 2 over 2. I can say tangent of pi over 4 is the y-coordinate divided by the x-coordinate. Since they're the same, it'll just be 1. I can say the cosecant of pi over 4, which is the reciprocal of sine. So it's the reciprocal of root 2 over 2. That will just become square root of 2. Then secant of pi over 4, which is the reciprocal of cosine pi over 4, also root 2. And then cotangent of pi over 4, which is the reciprocal of tangent of pi over 4, simply 1. And so by using geometry, we now have the ability to find the values of the 6 trigonometric functions for the angle pi over 4. Now, we can also do the same thing for these two triangles by squeezing them into the unit circle as well. So let's talk about that 30, 60, 90 triangle. If I make the triangle like this, so the hypotenuse is 1, and if I want this to be the 30-degree angle, we remember in radians, 30 degrees becomes pi over 6 radians. And so we understand that the horizontal, the base of this triangle, is going to be root 3 over 2, and the height of this triangle is 1/2, which means we have a point right here that is root 3 over 2 along the x, and then 1/2 along the y. So we could find sine of pi over 6, that would be the y-coordinate, 1/2. We could find cosine of pi over 6, which would be the x-coordinate, that's square root of 3 over 2. We could find the tangent of pi over 6, which is the y-coordinate divided by the x-coordinate. That becomes 1 divided by root 3, which we can rationalize the denominator to make root 3 over 3. Then we can say cosecant of pi over 6, which is the reciprocal of sine of pi over 6, 2. And then we take secant of pi over 6, which is the reciprocal of cosine of pi over 6. This becomes 2 root 3 over 3 when you rationalize the denominator. And finally, cotangent of pi over 6 is the reciprocal of tangent of pi over 6. This is simply square root 3. Now with this version, let's say, here we have the 60-degree angle in here, which you remember in radian measure is pi over 3 radians. The hypotenuse is 1 because it's a unit circle. The base this time is 1/2, and the height is the square root of 3 over 2, with this the right angle. That means this point right here, 1/2 for the x, and root 3 over 2 for the y. So we can say sine of pi over 3 is the y-coordinate, root 3 over 2. Cosine of pi over 3 is the x-coordinate. Tangent of pi over 3 is the y-coordinate divided by the x-coordinate, which is square root 3 divided by 1. Cosecant of pi over 3 is going to be the reciprocal of sine of pi over 3. That is 2 root 3 over 3 when you rationalize the denominator. Secant of pi over 3 is the reciprocal of cosine of pi over 3, 2. And finally, cotangent of pi over 3 is the reciprocal of tangent of pi over 3. The reciprocal of this is going to become 1 over square root of 3, which we can rationalize the denominator to make root 3 over 3. So now at this stage, we have the ability to immediately answer the values of the 6 trigonometric functions at pi over 6, at pi over 3, and from the previous case, pi over 4. So it turns out we can get clever with our 30-60-90s and our 45-45-90s to evaluate trigonometric functions outside of quadrant 1. So in this case, I have an angle labeled 5 pi over 3 radians with a point P right here. So what I want to do is I want to ask the question, what is the angle right in here between the terminal side and the x-axis, so that if I were to drop a line right there, then I could make this a triangle and perhaps use some logic. So it turns out this angle is pi over 3. And how do I know that? Because the full circle is 2 pi. Then if I subtract 5 pi over 3 radians, what's left over is pi over 3 radians, which we identify as a 60-degree angle. So we know that the base of this triangle is 1/2, and the height of this triangle is root 3 over 2, so long as the hypotenuse is 1, which it is because it's a unit circle. Okay, so then we say this point has an x-coordinate of 1/2, and the y-coordinate is negative because this point is below the x-axis. So we would say this is negative root 3 over 2. And then we can quickly evaluate sine of 5 pi over 3 is the y-coordinate negative root 3 over 2. Cosine of 5 pi over 3 is the x-coordinate 1/2. And we can keep going just for good measure. Tangent of 5 pi over 3 is the y-coordinate over the x-coordinate. Cosecant of 5 pi over 3 is the reciprocal of sine of 5 pi over 3. Secant of 5 pi over 3 is the reciprocal of cosine of 5 pi over 3. And then cotangent of 5 pi over 3 is the reciprocal of tangent of 5 pi over 3. This becomes negative root 3 over 3. So there we have it. Now it turns out we can use this kind of logic to evaluate these trigonometric functions at many, many angles, as long as they're related to 30 degrees and 45 degrees. Let's end today on something cool. So if we consider an angle T in the standard position counterclockwise by that much, we can also consider the clockwise version, so the negative version of the same angle. So this will be negative T, since we're going clockwise. And if I consider this triangle and that triangle, we notice these triangles are congruent, which means the bases are the same and the heights are the same. So when we go and we label this point P, we can call this cosine of T for the x-coordinate and sine of T for the y-coordinate. And then if I call this point Q right here, then this would be cosine of negative T for the x-coordinate and sine of negative T for the y-coordinate. We notice that this and this, the x-coordinates, are the same, which means that cosine of negative T and cosine of regular T are the same as each other. And this behavior tells us that cosine is an even function. Then if I look at the y-coordinates, point the y-coordinates right here, we notice that these are exactly opposites of each other, which means we can write sine of negative T is the exact negative version of sine of regular T. And this behavior tells us that sine is an odd function. And it turns out that because secant is the reciprocal of cosine, the reciprocal of an even function is also an even function. You can prove this quite easily. That these are both even functions. And so perhaps there are multiple odd functions, namely the reciprocal of sine, which is cosecant, is also an odd function, and tangent, which is sine divided by cosine. When you take an odd function and divide by an even function, you end up getting an odd function. Once again, not so difficult to prove. Tangent of negative t is equal to negative tangent of t. And then since cotangent of t is the reciprocal of tangent of t, then cotangent of negative t is equal to negative cotangent of t. So these four are odd functions. These two are even functions. So what can we do with this? Well, perhaps let's imagine that we happen to know, if we know that sine of 2 pi over 3 is the square root of 3 over 2, and perhaps we know this from our 30, 60, 90 rule, then we can say that the sine of negative 2 pi over 3 by the odd function property is simply the negative of sine of 2 pi over 3, which means this is the negative of square root of 3 over 2. And we can perhaps apply these properties in very fun ways. All right, so that's where we're going to cut the lecture for today, and we'll pick up next time with part 2 of section 4.2. Thanks for tuning in. Everyone take care.